Alright, hell yeah. So a commenter's like, hey, can you do this without using a solver? So we're going to do an iterative method. And this is kind of cool. What we're going to say is that kind of the initial setup, we're just going to assume that's going to be like the final shape that it's going to take. So we put an 80 Newton force on here, and we actually have kind of a wider angle. And that's a worse angle. It's going to cause more tension in the cable. Free body diagram shows that tension is equal to 40 divided by the cosine of the angle. And so when that angle is bigger, this number gets smaller, and that increases the tension. We go to our spring equation that says change in length is that tension divided by the spring constant. Hell yeah. And then we go to our final geometry that shows for sure the final geometry is this initial length, but then when we pull on it, we get the change in length, and it's going to be an addition of both of these. So this can be change in length divided by 2. So we say change in length divided by 2 is tension divided by the spring constant. The tension is this 40 divided by cosine, so we have that component. Going back to trigonometry, we see that the sine of this angle is the opposite. That doesn't change, divided by this full length. So it's the addition of the initial length plus that change in length divided by 2. And so we actually put that into here, and we just get one succinct equation. Alright, hell yeah, now you're ready to use this equation as an iteration. You're going to throw in the initial angle of 30, and then out is going to pop an angle of 20.4. Now that's much smaller, meaning your tension is going to be way higher. That's the interpretation of that. Throw in that 20.4, and then it's going to pop out 20.9, and that angle is actually a little bit more wide. Put in that 20.9, and then you actually converge on the right answer. You only have to do it about 3 or 4 times to get a hella accurate answer, and this was using iterations. So watch the full video to show you all the steps. Alright, hell yeah. So we have material mechanics, we have a 3-star problem. In the comments, someone's like, hey, can you do this problem without using a calculator solver? So we're going to solve this using an iterative method. So the first thing is kind of draw the setup. We have applying an 80 Newton force here. And what I'm going to do is like, hey, in the initial condition, when you don't have any force, this angle right here is 60 degrees. This is 60. Hey, this is 60. But what we're going to do is divide this into a right triangle. And so we're going to say this is 30 degrees. So remember that 30, because this is the angle that we're going to change. Now for this problem, a lot of people break it up into like 1/2. You know, but we're not going to do that. We're going to say, hey, we're applying an 80 Newton force, and then we're going to have a tension in the cord. Now these are going to be the same, and then keep in mind that the tension in the cord for this problem is what's going to change the length of the spring. So the equation for changing the length of the spring is the force inside the spring is going to be equal to the spring constant change in length. So we have basically 3 things. We can rearrange these any way we want. We want to solve for change in length. So change in length will be the force or tension in the cord divided by the spring constant. Alright, hell yeah. And so we're going to divvy in these angles. So we're going to have a 30-degree angle right here. Now I'm going to kind of go over this fairly fast, but we're going to sum the forces in the y direction. And so we're going to have, and that's going to equal, F equals ma. So in the y direction, we have the force in the y is equal to the mass times acceleration in the y. This is going to be 0. So now we can say, hey, I have an 80 newtons up, but then I'm going to subtract 2 times. And all we want is the y component of this force. So this is the x component, this is the y component. And how to do this quickly is be like, well, if this is my angle, the sun is shining on the sinin, so this has to be the cosine component. It has to be smaller, so I'm going to take this total force t, but then I can't multiply it. No, what the hell am I even talking about? No, if I wanted it bigger, yeah. So yeah, we are just going to multiply it. So how sines and cosines work, if I do cosine 30, this is a percentage of the hypotenuse. in that direction. So hell yeah. So we have 2t cosine 30. That's going to be this component. Booyah. And that has to equal 0. So we can rearrange this equation, probably get this over here, and then take 80 divided by 2, and then we're going to have 40, then divide by cosine 30. So the tension is going to be 40 divided by cosine 30. And this is where I was kind of going with it. If I have, if I'm pulling with 80 and I don't have any angle, the tension is going to be 40 in each. But because I have like a inefficient angle, and if you took this to the extreme where you like took the angles out like this, if you're a rock climber, an anchor like this would just be real bad. Even like that, if anything greater than 120 degrees is going to be even. You're pulling with 80, there's going to be 80 in that one and 80 in that one. You want at least 90 for rock climbing. But anyway, so to make... The reason that tension is bigger from this equation is you took that 40 and then you divided by the cosine 30. You're dividing by a smaller number, so this tension increases. All right, hell yeah. Okay, so then once we have the tension, we can put it into this equation and say change in length is that tension divided by the spring constant. And that's going to give us the total change in length of the whole bungee. Okay, so now we have to kind of go back to the original bungee cord, and for this problem we have this is 0.38 meters across, so it's going to be 0.19 meter on both sides, and then what else? This whole length is 0.76. Divide that by 2. Like one of these lengths is going to be 0.38. Okay, hell yeah. So now we have 0.38 meters and plus that extra. So we're going to actually increase this. All right, but before we do that, let's go back to figure out what's our equations for trigonometry. Trigonometry in this case would say, hey, sine of 30 is equal to the opposite over the hypotenuse. So we would have sine 30 is equal to 0.19 divided by 0.38. And that's what we get, because sine 30 is 0.5 and 0.198 divided by 0.38. 0.198 divided by 0.38 is 0.5. So there's a check. And if we change any of these sides, and how we would solve for the angle, we would do this, would be like, hey, this angle this is the angle right here, 30, is equal to the inverse sine of 0.19 divided by 0.38. So the equation, once we do change this length, and the change in length will be half. So this will be change in length divided by 2, and this change in length over here will be change in length divided by 2. So we'll have the angle is inverse sine of the opposite. Now this length won't change, but this will. So we'll have 0.38 plus change in length divided by 2. I'm not going to write that again, but I know that change in length is the tension divided by K. The tension is this 40 divided by K cosine of the initial angle. So my initial angle is going to be 30 degrees. So here's where we get into that iterative process. So my new angle, my angle after the pull, I'm just going to say angle 1, kind of for like, anyway, so we're going to have angle 1 is inverse sine of 0.19 divided by 0.38, and then this change in length divided by 2, so that's going to be plus 40 2k cosine initial angle. And hell yeah. So this is what we're going to iterate. And so for the, and k is 140. So let's throw this into our calculator. We're going to do inverse sine of 0.19 divided by 0.38 plus 40 divided by 2 times 2 times 140 cosine of 30. And hell yeah. So I feel like I did something wrong, but no, I think we're good. Hopefully we didn't mess it up. Okay, so hell yeah. So we get an angle of 20.4 degrees, and so now we're going to actually store that as theta. Cool, and then we're going to bring up our equation, and I should have just put theta in here because we're going to do an iterative process. So now now this angle right here goes into our equation, because we were just saying, hey, before we're even going to pull this, you know, let's say the tension was going to, what would the tension be? And the tension is going to be higher in these chords because the angle is worse. When you pull on this, the angle gets better, and if you pulled, if you didn't have any angle, there would be a 40 newtons in each chord, and you would have the least amount of change in length. Because the tension in the chord is only 40, your change in length, and we should probably already do that. So if we have 40 newtons divided by 140, the change in length would only be 0.28, 0.286. We've already done that one. But in our case, we're going to have 40 divided by 140 divided by cosine 30, and our change in length is going to be more, 0.33 meters. That's going to be the change in length. But we know that's not true, because once we do pull this, we are going to change in length. This angle is going to slacken, and there's going to be less tension in the cord to hold that 80 newtons. All right, so let's keep on with this iterative process. So we're going to throw theta in here, and booyah. So now theta 2 is going to be 20.9 degrees. I'm going to store that as alpha theta, and then just keep going. So theta 3 is 20.89 degrees, and keep going. Store that as alpha theta. All right, hell yeah. So we're converging pretty fast. Yep, so 20.88. So our angle, maybe 5 is going to be 20.888 degrees. Okay, hell yeah. So this angle is that. And now we can use this angle to figure out what our change in length is. Because now if we know that this is angle 5, this length did not change. So we're going to use sine of this angle. So we're going to say sine of this angle that we found is going to be 0.19 divided by this 0.38 plus change in length divided by 2. And so now we can just solve for change in length. Rearranging this equation, oh, I really don't want to do that, but I can get this upstairs, this downstairs, so that's going to be 0.38 plus change in length divided by 2. That's going to be 0.19 divided by sine of this angle. And now I'm going to subtract this 0.38, and now I'm going to multiply by 2. So hell yeah, so we have 0.19 divided by sine of that angle minus 0.38 multiplied by 2. And hell yeah, so our change in length is going to be 0.3058 meters. Alright, hell yeah. So I have no idea if I made a mistake, but this is the answer in the back of the book. What they actually want is to find this change in height. And so we can do that just by using a tangent equation. One, we need to know kind of what the initial height would be. And so this height, we can say a tangent of 30 degrees is going to be this 0.19 divided by that height. We can rearrange this. That's going to be 0.19 divided by tangent 30. And so this is our height. I'm going to store that as alpha h. And And then so with this angle, we're going to have tangent of that angle is 0.19 divided by this new height. I'm just going to say h5. And so we can rearrange for that, 0.19 divided by tangent of that angle. And so this is our new height. I'm going to store that as alpha g. And so we're going to have alpha g minus alpha h. And so that height change is 0.16879 or 0.1688. And multiplying by 1,000, you get 168.8. So that is the iterative solution, and it's just fascinating how this will converge just hella fast. This is the first time that I've actually done this using this half angle. I solved this problem in the video going for this angle. I was just more comfortable just knowing that this angle was 60, and then when we pulled on this angle was going to get bigger. But I can just do 90 minus alpha theta, and this angle is going to be 69.11. So in the video, this is the angle that I was going for. But in this problem, I set it up with the iterative method. And it's just cool. Some problems will iterate like this, and it's they'll just, like, putting in a value, you'll go from one anyway. I have a hard time explaining the iterative process, but but some problems like this, hell yeah, you throw in one and then it overshoots, and then you throw in that and then it undershoots, and it goes back and forth. And so and that is the case because we went from 30 degrees to 20.4, which is less, and then 20.9, which is more, and then 20.89, which is less. So yeah, let's take the last second to actually go through this. So we're going to 30 store it as alpha theta, and we're going to pull up this equation one more time. Okay, hell yeah. So we're going to go to 20.4, which is less than 30. Store that as alpha theta. Now we're going to go 20.9, so a higher number. Store that as alpha theta. And then I shouldn't say alpha theta, but anyway. So now we got 20.886, so that's lower. We're going to store that as theta. And now we have a little bit higher, 0.887. Store that. And now we have a little bit lower, because that was 0.8876. Now we have 0.8875. And so you see how that back and forth, that iterative process, and there's only a certain number of problems that will, follow an iterative solution in a simple way. I know using a solver method, I think it's like Newton's method of actually, you're kind of... like on the solver, you're asking for a low and a high because you're using the derivatives to actually find, kind of converge on a solution. Anyway, hell yeah. And I guess might as well end with that because, I think it's good to, so we're going to go over like this is what, y is equal to x cubed. And this is why on a solver it's just like, hey, you have to pick a point on this side of the solution and then over here. So a left bound and right bound. And what this says is, hey, this slope is going to be this way, and then this slope is going to be this way. And then we're going to get two new points right there, and it's going to be, okay, hell yeah, that's going to be my new point. That's going to be my new point. And then we're going to be like, hell yeah, new tangent this way. And then we're going to have a new tangent this way. So this one hella converges, and then just it's getting better and better. And so hell yeah, then we got it. But that in a nutshell is why you need a left bound and a right bound, yeah, so that kind of shows the iterative process. You need one solution to be undershot that gives you an overshot answer. Throw in the overshot answer to go back to the undershot answer. You know what I mean? But it'd be fascinating to kind of categorize all the problems that could be solved using a kind of iterative method without just like a straight mountain climber method. I remember like Price is Right, where you just have to guess back and forth to get a solution. You can always do that, but it's just kind of cool to have an iterative process that it converges And this one converges really fast. So hell yeah. So that's that in a nutshell. Thanks for joining me, and that's a video.